Okay, let's start. Good evening, everyone. So I think you can see my screen. Let's get started with the session 10. We are almost towards the end of the course, and today we are going to look at Rayleigh flows. Um, Okay, so by this point, I am pretty sure you must have seen at least one video recorded session of this live interaction series. No need to introduce the course name and the teaching assistant, but so I'll move ahead and get started with the recap today. Um, so what did we do last time? Was primarily Fano flows. Let me open uh, part of it to discuss a little bit to discuss the recap. Let me just open lecture 9 and see what had we had discussed. Um, okay, so Fanoflow had a interesting concept. See, if you think about it, we had studied, uh, we have been studying uh, primarily four types of one-dimensional flows. The first one being the normal shocks, the third one being, the second one being variable area flow. Then we studied Fanoflow, and today we are going to discuss Rayleigh flow. But in the video lectures, we have discussed these things. So primarily these four types of flows exist. And what is to be noticed here is in the normal shock, conservation equations give conserved quantities. Okay, in the normal shock, there is a transition that happens from supersonic to subsonic. So there is a directionality involved. Um, and we know that there are conserved quantities. What are these conserved quantities? It will be G, then P plus rho U square, and also H total, enthalpy. In variable area flows, in the next coming three flows, one of these conserved quantities get varied. So one of the three conserved quantities vary in the flow direction. Oh, I guess you're not able to see. Oh shit. Um, so let me move ahead. Yeah, so I was just saying that we have primarily four types of flows. One-dimensional flow, quasi-one-dimensional flows or one-dimensional flows. Uh, and accordingly, accordingly, um, we see that one of the three conserved quantities start varying in the flow direction. Okay. In variable area flow, the varying quantity is G. In Fano flow, it is P plus rho U square. In Rayleigh flow, it will be H total. So this is something that we noticed. So last time we did Fano flow, we saw that P plus rho U square, um, a quantity that can be given a name. I don't remember what name is has been given before. I don't recall right now. So we'll not worry about that. Um, Anyways, coming back, uh, then what we had discussed was, let me open lecture 9 again. So the next thing that we discussed was fan of flow. We started with fan of flow. Uh, we discussed the shape of a Fano curve, why with increasing uh, how do we get a Fano curve? How do we get the generalized shape? Something of this sort. Let me just bring that in the frame. So something of this sort was there, and then we also happened to see something of this idea. You see, okay. So going back. Hmm. It's not a good this thing. Anyways, so we saw H row curves also and HS instead of HS curves. That was one thing. Um, what else? Something of this sort. Some H row curves we had seen. Then we had discussed um, how this translates to. So how this translates to this. We kind of saw that. We also generated a Fano curve towards the end. That was something that we did. Then we did a small problem um, on Fano flows, I guess. Did we do this problem? I'm not sure. I don't think we solved a problem last time. Uh, yeah, not sure if we solved a problem last time. We happened to just do this Fano curve thing there. Uh, so today the topic is on Rayleigh flows. So let me just quickly um, go ahead and talk about Rayleigh flow. And instead of discussing things on Rayleigh flow, let's start with a simple problem on Rayleigh flow to get on with it. Um, so the first problem that we are going to do is, um, so let me open that problem. I'll jot down that problem. Okay. Um, let's get started. The question we have is we have to derive the formula for maximum that can derive for maximum heat transfer possible in a heated pipe if the given static inlet temperature is T1. Okay, so this is the problem. Let me just reiterate that problem, like restate that problem. Let me just see what are we looking at. Yeah. So or show that for a constant area. So area frictionless, steady, one-dimensional flow of a perfect gas, the maximum amount of heat that when added to the system is given by the expression. So the expression, I'm gonna just simply write the expression. Q max by Cp T1 is and just mm, square minus 1 raised to the power square divided by 2 and 1. So this is the derivation that we need, that we can uh, do. That will be our first problem. Just give me a second. This is all fine. What's going on here? Okay. Fine. So now, okay. So about this problem, this is a simple problem. If you think about it, it's not a very difficult problem. But to introduce or to just revise Rayleigh flows, we can start off with this problem. So we'll do that. So first of all, just like how we have been doing all these classes, we'll write the governing equations, and we know that this is a constant area flow. So G is equals to rho U, gonna remain constant. Just let me switch on these lights. Yeah. So G equals to rho U is gonna remain constant. This is conservation of mass. Again, because the flow is frictionless, P plus rho U square is a conserved quantity. There is no um, friction, and there is, however, some um, heat transfer that takes place, and that makes the conservation of energy not very useful because it has a unknown in its uh, expression. So a couple of things that are characteristics of Rayleigh flows is, let's start. So first of all, you see that there are expressions in terms of Mach number, um, and so you see the maximum heat transfer depends on the static inlet temperature and the Mach number. Uh, so let's try to derive every conservation equation into these two forms. So again, the first one is G equals to rho U. So rho U can be written as Mach times A, which is rho can be written as P RT, P by RT, and Mach number is fine. A can be written as SQRT gamma RT is constant, which implies that PM by SQRT is a constant. That's it. So this is something Okay, now we have P also in there. Well, we are going to use, so we can't just remove now, can't we can't substitute anything for P just from this equation. We'll use the other conservation of momentum equation to substitute P. So let's start with that. So we have P plus again P by RT. U square is Mach square and gamma RT. So RT gets cancelled and you have P plus this expression is a constant. You will have, I hope you're able to see the screen. Let me just check. Um, right. If you're able to see the screen, let me just check. Yep. So this is the second quantity we are going to use. This is the second conservation equation that we can use. We can't use the uh, uh, we can't use the energy equation for the simple reason that so we can't use the conservation of energy equation uh, because it has an unknown in it. So we are going to see derive this thing just using these two equations. Um, okay, so what we can do is substitute for P, and what we are going to get is M. So what is a nice way to do it? Yeah, M times 1 plus gamma M square. And let's take a square of this whole thing. Okay, so what are we saying? We are saying that for a constant area, frictionless duct, this identity is gonna hold. And let's use this identity to see uh, what is the maximum heat transfer that can happen. So obviously we know that the maximum heat transfer happens at sonic conditions. And so let's see what are the sonic temperatures and so on. So if I,
Sir,
yeah,
sorry to disturb. Could you please show the question again?
okay, okay. So the question is, I'll just try to explain it. You have a, it's a relay flow question. We are trying to just just get a revision of the entire topic. And so we start off with a simple problem that what is the max, we need to derive this expression for the maximum heat transfer that is possible. Uh, this is the formula, we need to derive it, or if I don't give this formula, you have to derive it just based on Mach number and static inlet temperature. So that's the question. I'll just wait for a second for you to be able to read it.
Sir, I took a screenshot right now.
Yeah,
Please see.
yeah. So the way we started was, I'll go one slide back. Something that you could notice about the four one-dimensional flows that we had been studying, the first one being the normal shock. We saw that we get three conservation equations, and they give you three conserved quantities. So you have mass velocity or rho u, then you have P plus rho u square and total enthalpy are the three quantities that remain conserved in the entirety of the flow. But then we start playing around with these three conserved quantities, and we see if we allow each of them to vary, we'll get a specimen one-dimensional flow. So for a variable area flow, G starts varying, whereas P plus rho U square and HT remains conserved. In Fano flow, this uh, P plus rho U square term does not remain conserved because of the frictional effects. And in Rayleigh flow, we will see that there is a unconserved total enthalpy. So again, just conservation equations using the first two equations. The third one we can't use because it has a unknown in it. We can't use it as such. So just going by that, using these, expressing them in terms of Mach number and temperature, we derive these two expressions. Now simple substitution we'll do, and we get this expression. Now I'm just gonna write what is the T star, because we know T star corresponds to maximum heat transfer. No matter if the flow is initially subsonic or supersonic, the maximum heat transfer possible is will stop when there is sonic conditions reached. So with that, let's start writing the expression for this thing. So you have T star, and you will get to know that this is 1 plus gamma. This thing is there. Fine. So what essentially we have is T star by T is 1 plus gamma Mach square square divided by 1 plus gamma Mach square. So this is also square and this is also square. That's it. So this is the formula we have got. Uh, but we'll note that heat. So now the heat transfer, if I write Q max, that is Cp T total at sonic condition minus T total. Okay, just a simple solution. You can take T1 common from this. T1 is the static temperature. So mind that. So you will have T total times T total times T1. And let me just put this thing there. Maybe I can take this entire thing out and written as 1. And this is okay. That's fine. So use this expression. What do we have? So let's write what this expression would be. Just a second. T1. Actually, you can write it this way rather than T star and then T star by T1. T total 1 by T2, T1. This one is okay, right? Yeah, this one is fine. So we can use we will first write what is this. That is gamma plus 1 by 2. You're able to understand why this is gamma plus 1 by 2? Or if I don't write it this way, let me just straightforward. right? So just if we substitute mark equals to 1, we'll get this. It should be gamma minus 1 by 2. Now just let's substitute these things. We'll get Q max by Cp P1 is what? Start substituting things. Hmm, we'll get gamma. This thing is there. Then we'll substitute this. Then we'll have minus 1 minus this thing is there. Um, See this gamma plus 1 by 2 will get cancelled. You can just have this term. So we'll have this expression there. And now it's just one more line of substitution. So let's just do that also. So you have terms from here. So minus 2m square minus 2 gamma m square. Then this will become gamma minus 1, gamma square minus 1, because see, this gamma plus 1 will multiply with this gamma minus 1. So you get gamma minus 1, gamma square minus 1. And you have Mach square. So Mach to the power 4. Mach number to the power 4. And that's it, right? Just a simple expansion. So this one can be written as 1 plus gamma square Mach to the power 4 plus 2 gamma Mach square plus there is a minus sign. See this one and this one gets cancelled, and if you look at this one, this is plus 1, isn't it? Yeah. So this term will also get cancelled with this term. So what you will have is mm, this thing there. And this is basically 1 minus Mach square to the power square. So we've gotten that expression which we had started, which we had needed to derive, right? Simple stuff. Simple stuff. Yeah, that's it. Great. Fine. One more thing that we'll do is there is another simpler stuff, like simpler question. Let me just write that too. Yeah. Yes, you see the
Sir,
blank slide, right? So
yes,
that
yes. Sir,
maximum.
I actually
Yeah,
had some doubts in the one of the previous assignments. When can I ask them?
you can ask them now. I'll stop this. Hmm. Yeah.
Um, there were actually two questions. I think fan of flow assignment.
Hmm.
In that assignment, can
So that assignment is submitted and this thing, no,
yes,
this
yes, it
and
has
evaluated as
it was
well.
evaluated. Yes, yes, it was evaluated.
So
There were
let me
I
wait.
think
I'll start sharing that assignment. I'll try to share that assignment. Okay, you can go ahead and try to explain it while I open things.
no, there were like three questions. Like there was CD nozzle, then there was a uh, uh, rough pipe connected to it.
Hmm.
So there were like three
Hmm.
questions of like similar fashion. I was able
Hmm.
to solve the first one.
Hmm.
There were like normal shocks in this configuration. In the first question, it was in the diverging section of the nozzle. In the second, it was
Hmm.
in the rough pipe, and in the third question, there was an oblique shock. So
Okay, outside.
they told to yeah. So so they told the questions the all the three questions were in that question we had to find the P naught, that is the reservoir stagnation pressure. So I was able to find it in the first question, but not in the other two questions. I tried them.
Uh,
Don't
is
know
it
what
possible?
would
I
happen.
don't know. Why am I not able to see? Am I not able to see this thing? It's
What's that?
wrong. The scores I'm not able to see suddenly. Let me try this
Maybe,
NPTEL thing again.
i-
Do you
in
have
the
this?
Cesar, in the on the
You wanna
website,
share the screen?
top right,
Huh.
actually I'm on the phone. No, no, in the on the website, yeah, yeah, to the right on your email, I think you can there is a drop down menu. You can see
Wait,
my
I'll
course.
try to. Yeah. Yes, you're sharing something? Oh, you
No,
share.
no,
No, you're not sharing anything.
I'm not. I'm not
Wait,
actually
wait,
in my
wait.
smartphone.
Hmm. Wait. Let me see if this we can. Yeah, good. So week 9 assignments. Okay, is it? I think in the last towards the end. I think these are the questions,
Yes,
right?
yes. Yeah,
Okay,
this question.
okay,
Uh,
okay.
eighth and ninth, I think. Yeah, eighth and
Eight
ninth.
and nine. Okay.
Yes,
Observe carefully. So we'll start with this. These are connected questions. Is it? Consider the following chamber of the flow in a
no,
convergent
no, no.
divergent nozzle.
That's not connected.
Then okay,
No,
they are not
they are
connected.
not
We can just
connected.
start
Yes,
from eighth.
yes,
Observe carefully
yes.
the given figure. Calculate P naught at which the given condition holds. Gamma is 1.4. Throat is this. Okay, so what does it say? P naught T naught. Then there is a area ratio. Fine. Then you have a shock wave at 100 mm. The diameter is 50 mm. Friction factor is given to you. The length is 250 mm. Okay. Then ambient pressure is 1 bar. Okay, so you were able to do which one? Seventh one, but not the eighth one.
Yes, I was able to do that.
Okay.
First one, so the seventh, but not eighth and ninth.
Okay. Why? Where did you so okay. So let's
So
discuss the approach. Hmm.
actually I solved the eighth one. I got
Hmm.
something 4.35 bar. It was really close
Okay.
to 5 bars, so I marked 5 bar, but the answer was 3 bar. I don't know
Okay.
what went wrong.
What about the ninth one?
I don't know about what went wrong there. I got a really weird answer.
Oh, you got a very weird answer. Okay.
Yeah.
So how did you solve the eighth one? Let's discuss it. What was your approach?
So my general approach is like I will consider the outlet from the rough pipe to be like what we say, ideal, or I
Smooth.
don't
Yeah.
know.
So like it's
Yeah,
the
so
pressure is smooth. Yeah.
the exit pressure is 1 bar, so it's equal to ambient pressure. So I took pressure ratios uh, across. all the sections, like from the exit to just exit, then the normal shock, then I came till the exit of the CD nozzle. So I calculated the pressure at that point, uh, like
Okay,
at
at
the
the
exit of
entrance
the
of
nozzle.
the duct,
Yeah,
entrance of
yeah,
the duct.
entrance of the
Okay,
duct, and that's the actually exit of the nozzle. So I can calculate P naught from that point. So from the isentropic equation relations. So
wait.
um,
So yeah, okay, fine. Hmm.
so
Okay.
I got the pressure at that point. So from that I got the
Hmm.
P naught. The P naught I got was 4.35 something bar.
P naught. Where did you get the P naught is 3.4 bar? Where at the entrance of the
No, no, no,
duct, is
no, no.
it? Okay, at the
Yeah,
exit of the.
at the exit of the nozzle or entrance of the duct.
Okay, we
So
got it. You
that's
you
the
got a
same
P
thing.
naught value.
Yeah,
You got a P naught value. Okay, fine, got it.
yeah,
Okay, the reservoir pressure you got directly. Okay, wait.
yeah.
So, you have your numbers with you from for that, or do you want me to try to solve this problem?
Just give me a moment. I have it written. Hundred
So P by
point five. Yeah,
uh,
yeah.
if we
I got the mark numbers at the different sections. At the
so do you have a mark number at
entrance,
the entrance of the
yes,
duct?
yes. Yeah, at the entrance it was 2.95. Just before the
2.95.
normal, yeah, at the end, at just before the normal shock, it is 2.175. Uh, After the normal,
2.175.
yes, 2.175.
Hmm. Hmm.
Then after the normal shock, it's 0.55, and at the exit, it is zero point 0.6.
P2 minus P1 plus rho U1 square minus rho 2, whatever the difference is, FL by D, rho U square,
Yes, yes.
or what is it? What's the formula for it? Let me check. So 9, the formula. Yeah, rho U square by 2 FL. Yeah, you use this. Okay. And you can also use the tables, right? We need to use the tables. Don't need to do that.
Yes,
Okay, so let's start. See, so the area ratio is 1 by is 4, right? So if I open the tables, we open the table for 4, right? Corresponding to 4. It's
yes,
2.995 you got, right? 2.9.
yes. I got
Yeah,
2.95.
2.95 is fine, or 2.94 is also okay. But yeah, so at least your that pressure is this mark number is fine. Um, then we can switch to I guess we can switch to fan of flow. If I go towards fan of flow, so fan of flow corresponds to uh, so we have 2.95, right? So you're able
Yes,
to see the
2.95.
screen also. So we'll use
Yes, yes.
FL max by D for this thing. So 2.95 is what? Uh, 5, 3, and 6. This is what? 99, 45, 0.5145, I guess. So mark number, this is FL max by D is zero point 0.5, right? The value is right? 5145, right? 0.5145, this value. So I'm gonna use this. So after the shock, or let's say so FL by D, right? Wait. So where's the problem? So what is the F delta L by D? What is that value? This is 0.02 times 100 mm, which is 100 into 10 to the power minus 3 by 50 mm is again 10 to the power minus 3, so 10 to the power minus 3 pencils. This is 0.04, right?
Oh, yeah.
F
Okay,
delta L,
okay.
F delta L by D is what? If calculated it, 0.04. No?
It the length is 2500. Okay,
Like
wait.
I am trying to,
Yeah,
so
yeah,
what
yeah.
I'm
Zero
doing
point.
is
Yeah,
from the inlet of the 0.04, right?
yeah.
No? So
Mhm.
then this one will be 510. No, wait. 5145, right? So this one will be what? 4745 FL by D. So at the inlet of the, sorry, at just before the shock, the FL max by D value should correspond to 0.4745, right?
Yes.
Should I? Right, yes. Let's
Yeah.
see. 0.4745. So we were at 2.95, I think. Yeah. So now 4745. Let's say 2.71. Wait, so your mark number was
Huh?
2.175, is it?
It should actually decrease, right? The Mach number should decrease. Yeah. Oh, what did I write? 2
So let's
I think my Mach number is wrong. That's why.
so how did you solve it? Maybe there's a problem
Actually,
there, or maybe
I
hmm.
I actually directly use the formula, the whole huge
Okay.
formula. Yeah, from that I got 2.175.
Okay. Okay. Hmm. So one good way to do like these Fano flow and Rayleigh flow is um the logic for like I don't know, don't need to tell you, you already know, but let me open the slide. So the whole point is like such kinds of problem. I don't need to tell you, you know it already, but still, for the sake of whatever, let me increase this. So what I was saying was, no, you're not able to see it now. Wait. So
No,
I'll
I
share my
can. I'm
screen,
seeing the
right? I'll
table.
share my, yeah, yeah. I'll share my screen. So with these, even with the variable area flow, so I saw that the way I had been discussing, um, now it's visible. So the way I had been discussing this entire thing uh, was trying, like it is a little, I was trying to complicate things. Well, if you have a flow out, non-air flow, if your gamma is different, then things change. But the whole point of normal shock, or see, the whole point of these problems where you will have a combination of different features, just like how I discussed, there are a couple of things that we may note down to try to solve this problem. First of all, a normal shock does not affect, so it does not change the Fano curve. So, like how we discussed last time, uh, I can't draw it, right? Wait. Uh, yeah, you're still able to see this thing, isn't it?
Yes, I can see
Yes,
the PPT.
yes. What I was saying was, so no matter if there is a normal shock in between a duct of with friction, you will still stay on the same Fano line. So no matter, so it was something like this. So variable area flow comes like this. You have a stagnation condition, then it comes down like this. Then you go a little up because there is Fano flow obviously, and now you get a normal shock. So this normal shock will be dashed. I am not drawing the dashed lines, but you consider it, but it still stays in the on the same Fano curve. Why? Because as we discussed, along the normal shock, all the three quantities remain conserved. That's the idea. Along a normal shock, both all three conditions remain conserved. So now how do we, the easiest way to do this thing is that we should note that along this curve, the T star values, the star values, sorry, not the T star, the star values are the same. No matter what, on what branch you are, the star values, P star, T star, uh, P naught star, they will remain the same. So what we can use is, now if I go back to those tables. See, these table corresponds to star values. These are the reference conditions. So we can still use the same values. So like no matter like we maybe we did a mistake in calculating the mark number before the shock, but if we had done that, we could have used the same. Suppose this is the FL max, right? After the shock, to get the to get the mark number behind the shock, we can use the normal shock table. But then again, because this star values are the same, we can use that value to calculate things. So you get my point, right? So if this one is suppose
Yes.
2.75, right? 4745. So let's say mark number is 2.71. Now let's go to the normal shock tables. So I'm just like trying to tell you how can like what is the simplest way out there.
Sir,
Huh,
uh,
have a doubt.
no, no, nothing, nothing, no, no, nothing, nothing. Sorry, no,
No, no, you can still ask. No issues.
no.
2.7.
And I was thinking that that we took actually 250 while calculating the uh, 4FL by D. It should
Ah,
have been
okay,
100.
that is also a thing, no? Four times.
Yeah.
4 FL by D. Yeah, that
4F.
is also an important. The problem is it's not known, no? Which if it's a fanning factor or what is it, right?
It was it
That
is
may be.
0. That's actually the fanning factor. Because I use
Is
the
it
same
written
thing.
there?
Uh, what is the question? Yeah. Uh,
So
yeah, they have F bar is 0.02.
F bar is 0.02, but is it is it Darcy friction factor or is it a fanning friction factor?
It probably it should be because I solved the because both the
Solve
seventh
the
question
seventh
is
one.
having this same F value. So I got right answer for that question. So I think that's the basic factor.
Wait. Then let's think about um. Wait.
I
Where is it?
actually
Where's
plotted
the
that
in this
equation.
one? Hmm.
I got it. I am again getting 2.175 for just before the normal show.
0.175, is it?
Yeah, means
Maybe I have a
I
solution. We can
used
check.
actually
We can check also. Wait, I have a solution. That solution might have this thing. If it's a friction, generally, how do they use it? So, so they use it 4 FL by FL max by D. Okay, so four times, right? Which is fine. So we can use four
yes.
times. Okay, so if I go back and use four times, right? All this one first, let me go back to the question. Yeah, that is something. So, is it like this 4F? Is it always there? Like I'm not sure. Is it always 4 FL by this thing?
What's
Let me check in the book also. Is it always 4 FL by
uh,
max? Or is it FL max by D? That is a little, it's a matter of
according to the
consistency.
formula? Yeah, it is 4FL by D. 4FL star by D. Yeah. The formula was like 4FL by D equals 1 by M1 square minus 1 by M2 square by gamma and all some.
That's fine. The
No,
problem
no.
is
In the tables,
which F it,
the
this
table I'm
table
having. No,
you're
no. In the
having.
gas, in the property tables, they have mentioned 4FL by D.
Okay, so corresponding to
At
that, you
least
check
in
what
my
mark number you get. So check what mark number you're gonna get.
Just give me uh,
See, if you look at my screen, this one uses spanning friction factor. And what you have been using is Darcy friction factor, isn't it?
okay, I think maybe I'm making a mistake there.
No, no, check no. You check what so in your table you have a table or like hard copy or soft copy.
No, no, I'm having soft copy. Uh,
So share your screen, no?
uh,
That's
Actually, it's on another device. I'm not having it on phone.
it's another device. So wait.
They
So
have it. The table says that it is 4FL star by
which is
D.
fine. Yeah,
Yeah, but the F it is not F bar. It's actually F.
it's
Just now.
what? It's what?
Maybe it's just F. It's not F bar. Maybe.
It does not matter. It does not matter.
Okay.
Why it does not matter is because we are considering f remains constant. So f bar will come out to be equal to f. Yes, like in this question, because there is no variation given in friction factor, f bar has to be equal to f because f is a constant. Get my point? You tell me, wait, so
Okay.
we were at 2.95, right? What 4FL by
Yes.
D value you
2.9.
have?
So
2.95 or whatever.
2.95. I have 0.5129, 0.76030. Yeah,
So
point 5145. Yeah, 5145. I have
five
the
and
same value.
five and same values, no?
5145.
Now,
Yeah. But
now,
the table you are having, it says that it is FL by D. Maybe my table
because
is having
these
another F.
friction these friction factors are different. Forget about my table. You consider your friction, your formula. So now in your formula, what is 4F L by D? Forget about my formula.
Yeah,
What is
for
4F?
2.95, for
Uh,
2.95, I am getting 0.5145.
5145 is
And
fine. Now what is your 4F L by D?
oh yeah,
F4F
for into 0.02 to I was getting 0.16. 4 into
be
0.02,
point 16,
100
huh?
by 50, 0.16.
Point
0.16.
16.
Yeah, according for 100 mm. Yes, 16 and 0.5145 minus 0.16. It's
Let it be. Let's. Hmm. So,
0.3545.
so you subtract that value and get what is the mark number you get?
Point, I will get 0.3545. Yeah, I'm getting it 2.16
2.17.
between 2.16 and
2.16, right?
2.18. Yeah,
Great.
maybe
You're getting
2.17.
2
It's
point,
between.
2.17. See, I have
Yeah.
the solution also there. So what is this final value do you get? 3.29. Yeah, which is closer to 3, not okay. Okay, let's continue. So you are getting 2.17, right? Let's go back.
Uh, yes,
2.17,
2.1.
right?
Yes, just before the normal
Okay.
show.
Okay, now we'll go to the this one normal shock table. Tell me then after what do you get? After the normal shock, what is the Mach number do you get? 2.17, right?
Uh, one
Two
and two.
point.
I get 0.55. Yeah, it's the same
So
thing.
you'll get
0.55.
point five, not
55.
0.55. No, no, no. Get
M.
0.512, which is also close to
Okay.
four. Yeah, 0.55, right? Fine.
Yeah.
Now, there is additional this thing.
Again, a fan of
Is additional duct. How
yes.
much is left? 150 times 150 mm.
150 mm.
150 mm, right?
Yes.
Uh, Now just go to your 0.5512 table in Fanoflow and what is your FL max by D? 4 FL max by D in your table. So 0.55, right?
It's between point seven, point 7866 and point 6736. Point
This is
seven eight
8 and
six
3.
six.
So 11,
Point
5,
36.
73, 0.73 loosely.
Yeah, 0.7286. Yeah. Okay. Got that.
0.7286,
But,
huh?
yeah.
0.7286. Okay. Okay. Now what
It's,
now let's calculate what is 4FL
it's
delta L by D. So it's
0.7286 minus
0.08
0.24.
150 mm, so three times
Point four
0.24,
eight point. So finally, I get
0.24,
0.4866. 4886. Yeah, after subtraction.
0.4866, 4886,
4886. Yeah. 4886.
0.4886.
For point four
Okay,
eight eight six zero, can I get 0.4941? Yeah, nearly point 61. Nearly
0.61, huh?
point six
So
zero.
your mark
No,
number
point six point
point
six point six.
point 0.6, exactly point 0.6, huh?
Yeah, yeah, point six. 0.6000 something like that. I
Yeah, yeah, fine. That's
it's
okay.
not mentioned.
Okay, so let me see if your mark number values are fine or not. I think it's pretty much right only. Some other error you have done. Now your 2.17 is 5.55 is also okay. From fan of flow, this is there. 0.24. Okay. A mark exit is 0.43, huh? This is wrong. It might be 0.43. Maybe there is an error in the solution itself. You'll have to correct that. I'll check this thing. Maybe you got your answer right. This is wrong. Because every time this some TA will solve it. And I think you're able to see my screen, right?
Yes, yes, I can.
Yeah, so there is a small error, I think. So this one is wait. So what this guy has done is see what he has done. He subtracted P by P star minus 0.242. 0.24. This is an error, no? Why is he subtracting this 2.012 from this value? That's why.
And surprisingly, for all the three questions, uh,
Ah,
the answer is the lowest P naught value in the options also. I don't know.
that's 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 just a coincidence, I guess.
Yeah, yeah, coincidence, but yeah, I was able to see.
Yeah, so maybe this thing is okay, fine. Let me see if with the other question also there is some error. Well, we'll have to solve it to see if there is an error somewhere and directly see. 513. Maybe this one should be fine. Let's see which what is the ninth question.
That's an oblique shock question.
Hmm. And you have been given a angle 60 degree. This is
Yes.
it's a shock wave, huh? Yeah, it's a shock wave. Theta is 60 degrees, and you have to calculate this theta or this is beta. This is beta. This is not theta. Yes, this is beta value. This is not theta value, right? This is
Yes. Yes. Theta.
that one free pressure boundary. And this is ambient. Okay, this is yes. Okay, so now how do you solve this one? Uh, let's start with
It's
this one
nearly
again.
half the question is same. So at the
Half
inlet
the
of the duct is 2.95. So you just have to calculate
yes.
the exit of the duct Mach number.
Yeah.
Then
So what did you get at the exit of the duct? We can get
uh,
a value, right?
just, let me see.
Mark num-
I'm not able to find that solution.
So 0.5145 minus 0.02 into 4 times 2 into 5. This is 250 by 50 is 5 times. What is this? This is 20. This is zero point 0.4, I think. No? Zero
Yes, that's
point 4,
4
no?
FL by
F
right? Yeah,
4
that's
FL
fine.
by delta L
Yes,
by.
yes.
So when you subtract that value, to you will get 0.1145. Now if I go back to the table, 0.1145, and we'll have to get wait. More thing is it's the subsonic flow, supersonic flow. This is a supersonic flow. Okay. Supersonic flow trying to come to sonic conditions. 0.1145. 0.1145 is also fine, no?
So
Mach number is
1.45 nearly. Mach number
yeah,
identity.
1.44, let's say.
So
Now we are
4
getting
1.
a yeah, 4544 is okay. That's okay. Now we have to go to theta beta m tables. Let me go there. Let me open a table there. Theta beta m table. This is chart, not a table. Your table. Think I have a table for this. Or let's say let's use this table on this chart only. We have a beta value, right? We have a beta value,
Is 60 degrees.
right? Beta value is 40. Mark number is 1.44. Wait. So beta value deflection angle. This so if I look at this, you can see my cursor.
Yes, I can. Yes.
This is 1.44. 1.44 is less is higher than 40 degrees. It was 60, no, it was not 40, it was 60 degrees.
It was 60, yeah.
Yeah, it was 60. 60 is fine. So 60. Let me copy paste this thing. If I go here, yeah. Hmm. So 60 is this. We are looking at something 1.45 we look at. This is now I don't know what value this is, right? So I have to copy paste something bigger. Well, you have a value. Do you know what deflection angle this is? Because we'll need the deflection angle, right, to solve things. This is 1.45. This value. We're getting something close to 9 maybe. So this is 10, something close to 9 degrees. So this is our, what is it?
Using calculator, get 9.4 something.
9.4,
9.4
huh?
degree. Yes, turn angle, right?
Yes.
Yes,
Yeah, the
9.
deflection angle. Yeah.
Yes.
So now we have M and 1, right? So we have M1. Now we have this deflection angle also. So if I have, so I have M1, let's say, yeah, fine, that's okay. Is 1.45. Okay. Deflection and let's use the same thing. This is 9.4 degrees. Then MN1 is, uh, can you calculate what is the sine of 9.4? Sine times of 9.4. Let me open. Did you do it this way? These are the values
Uh,
consistent with your solution? You're not sure.
I'm actually not finding the solution.
You're not
Uh,
able to find a solution. Where did you
no,
got
no, no,
stuck?
no, 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 no. I wrote the solution, but I'm not able to find it right now.
Ah,
I
okay, okay. That's okay.
wrote
So
it
let's
somewhere.
try to solve it again. Yeah.
Yes.
Let me open this graphing thing or maybe use calculator. Just tell me what is MN1.
Uh, MN1
1.4
is
times sine.
1.4 times sine, right? That's one times. Yeah. MN1 is one is point 235. 235.
Is it a value lesser than 1?
Yes. 1.44 sine 9.4, right?
Hmm.
It's 0.235.
0.235. Where am I making a mistake? Hmm. Is it sine theta minus beta? Something of this sort. Remember, let me see the formula. Okay, this thing has gotten stuck. So you can check the formula, no? You also have a soft copy. What's the formula Mn of Mn1? Is it sine theta minus beta or something? Is it the difference? What is it?
Um,
It might be 60 minus 9.4. Not sure. I'll have to check. My computer have gotten stuck, so I'll just wait till it responds. Meanwhile, you can tell me.
just give me a moment, I'll have it.
Wait, I'll open it. Listen, yeah, this is not gonna be anything. Wait. Did this in lecture 3 or lecture 4? Somewhere there. Normal shocks. Not normal shocks. About this. Oblique shocks and expansion. Yeah. The formula
MN1 is
is
M1 is sine beta. Beta is 60. Yeah. Should be sine 60.
sine 60. Sine 60 is root 3 by 2. This is 1.45. Root 3 by 2 is what? 1.7. Wait. Yeah.
We get 1.247. MN1
1 point,
one is
1 point,
1.247. 247.
1.247, huh?
Yes.
Okay. So now just use the table to find the subsonic MN2. So I have this all charts. 1.1.247, no? Or what was it? I forgot. 1.247,
Yes, yes,
no?
1.247. Yes,
So Mach number will be point closely 0.81. Mn2.
point,
This is
yeah, point eight
Mn2
one.
is 0.81. Now you divide it by sine 60 minus 9.4. 0.81 divided by sine 60 minus 9.4 is how much? I'll use my mobile.
It's 1.03. 1.03.
60 minus 9.4 is 1 point. No, no. 0.81 you took, no? It's
Yes,
1.04.
1.6. Okay, 1.0. Okay,
1.048.
1.035. So 1.04. Okay. Okay.
What value you are getting? Tell me.
I'm getting 1.0335, 1.34 nearly.
1.035,
Zero
right?
three. Yeah.
So now what we'll use again. So now, uh, yeah. So now you find P total 1 divided by P total 2 in the table. Let's open the table back. Open up now. Yeah. So 1.03 is this. P total by P total 1. It's close to 1 only, right? It's close to 1. So this one, let's go back now. Now we'll have to go back. So this outlet pressure is close to 1 bar. Now, uh, wait, yeah. Mm, this is 1 bar. So at the exit of the duct, it's close to 1 bar. Outside, now, can we use that P star equals to A star? No, we can't, no. Yes, we can't use that. Now we'll have to find from we'll have to go back to Fano flow tables. So Fano flow tables, we have Mach numbers, right? I don't have the Mach numbers with me. We can use this P naught by P naught star values. So you can find out. So what was the Mach number at the exit of the duct? Can you tell me again? I'm not.
Was
It was
was it
1.45. One point.
before shock?
Yeah, yeah. Before oblique shock,
Yeah, it was 1.45.
right? So now
Yes.
1.45 corresponding to that value, we will find P naught by P naught star so that we can find out the P naught star value. 1.45. So this value is close to 1.14, right? 1.14, and P naught star will be 1 bar divided by 1.14. Now, what was the Mach number at the entry? It was 2.95, right?
Yes, 2.94.
2.95. 2.95. The P naught by P naught star value is close to 4, right?
4, yeah.
So
4,
P
4,
naught
4.
by P naught star is 4. So what is this P naught value? 4 divided by 1.14. I'm doing this on my like on notebook or something. I'm not showing anything on the screen. So what is this value? And now P naught remains constant across the converging diverging nozzle. So 4 divided by 1.14, which is 3.5.
3.5, 3.508,
Have we
0.508.
made a big mistake somewhere? Let's see. What error have we made? None of these options are so low. So 2.95 is okay. Mark number is this 0.22. 0.226. What is 0.226 about this? 0.95. Okay. 0.95 might be 4.05 or something. What is this 0.226? Yes, you're able to see the screen, right? What is PA by? Okay, this is the static pressure. Mm, from oblique shock tables, you get P2 1.647. We didn't get this number, right? 1.647 we didn't get. We got 1.00, no? Angle of 60. A mistake there. Mm, So what did we do in the theta beta diagram? Theta beta thing there. Just have a table. Theta beta table I don't have. Do you see any mistake we have made somewhere? Or just give me a second, I'll open the
Um,
theta beta.
I generally the way I solved this type of question was like I take the static pressure ratio and then in the last I just convert the uh, s- I just take the isentropic relations into the picture.
That's
So,
fine. There are two things. First of all, let's talk about that. See, there are oblique shocks, right? At the end of the at the end of the ducts, right? So which means that this P naught, see, P ambient of 1 bar is the stagnation pressure, right?
but
Isn't it?
can
It's the
we
sta
uh, we can uh, use the static pressure ratio, right? In this
we can
case,
use it, but the question is if the ambient pressure which is given 1 bar, is it a static value or is it a stagnation value? You can use the
that
static value, but if you're multiplying anywhere the ratio between static and stagnation pressure, then it is essentially using stagnation pressure. It's the same thing. We can do it multiple ways. But the question is it a stagnation value or is it a static value? What do you think? I think it's I've been using it. This one
it is it is stagnation
is
and static at the same time because air is actually stagnant, but maybe due to some entrainment due to the flow. Mm. But P ambient won't change, right? Because it's ambient
P
pressure.
ambient won't change. P ambient is actually the stagnation pressure. It's just like one from one reservoir to another reservoir,
Is
right?
yeah.
So even if you use static ratios, you have to somewhere multiply static to stagnation because the only value that is given to you is stagnation value. It is not static value. So you will have to somewhere use the ratio between stagnation and static. That is fine. Now 1.44 Mn1 is let's see 1.44 till 1.44 everything is okay. So 1.44 times sine 60 is 1.24. 1.24, no? Yeah. And
Yeah, 1.247.
okay. So if you have 1.24, then going to the normal shock tables, 4 gives you 0.8183. 0.8183 divided by sine 60 minus 9.4, which is 1.05. Okay. So now M2 1. 1.05. So you use stagnation static values, right? You use P2 by P1 here. You can see my screen, right?
Yes.
You use this value. So you are also getting M2 as 1.05, right?
Yes. Nearly. Yes. Nearly the same. 1.04 something.
Yeah. Now you use this P2 by P1 value, or you use this one.
I took the P2 by P1. I don't take the total pressure values. So
But do
it's
you
like
know
it
P2? But do you know P2? What is the P2 value?
P2 is I
We know PT2. Do we know PT2 or do we know P2?
mm, there is the stagnation pressure, but it is
It is not
but
static pressure.
maybe that's the issue.
No, but
It's,
even then you are not getting something is wrong still. So
give me a moment. I'll solve it with the static pressure ratio. Maybe
those are also like it's 1.05 and it's 1.00. So it does not matter that much. It's only a 5% error, maybe even lesser. I don't know. Hmm. Okay. Total pressure behind above the thing is there. But this value, how does he get this number? Why is it not responding, man? Yes, Pranav, you tell me, what are you thinking?
I'm actually
Uh,
trying it with the static pressure ratios. Uh,
you're trying with the
uh,
static pressure ratio, is it?
yeah, yeah. Maybe I'll.
Okay. Still, you will not get that high pressure. Did we make a mistake somewhere? Let's see. Solution says hmm. There may be one mistake that we have done. You see, that I don't know. I have not. See, the flow is getting compressed twice. There are two shock waves.
Okay, but
So if I
uh,
think the
uh,
flow gets compressed like this, and then goes back. Okay, so we have to do it twice, not just once. Hmm. That is something that we didn't consider in the first go. We just considered one shock wave, right? Have to consider twice. 1.44. Let me check the formula for Mhm. Even behind the shock, the flow is close to sonic conditions. Okay, Pranav, you tell me what pressure you're getting at the exit of the duct. Are you getting a different value? I'm getting a low value.
Uh,
Mm,
Give me a moment. If the exit means just before the shock or after? Okay.
just before the shock.
Okay. Uh,
Okay,
where's it?
one more thing, man. Is there something wrong or if I'm making this correct? I think. So, okay. This theta value of 9.4 is fine, or have we made a mistake there as well? The value of deflection angle is this thing. One shock wave is at theta angle. It's 60, 1.45 Mark 1. Yeah, that's fine. Deflection angle we get
I'm
9.4.
getting a 0.3 degree difference, but that won't make any change.
You're getting what?
Just a 0.3 degree error. It was 9.7 actually, maybe.
You're getting 9.7. 9.7 as in what? What is this 9.7?
Degree for 3 times. 3 times.
9.7. Okay, okay. No,
Uh,
what was your stagnation pressure just before the shock?
and I didn't calculate that. Um, hmm. But we need to do that uh, calculation two times, right, for oblique shock, because we get a reflected shock.
Just for the first shock, because see, at the inlet it's 1.44, right? Mark number is 1.44. That much is fine,
Yes,
right? Then once we calculate M2, how much you're getting? It's 1.0 something, right? 1.04,
1
isn't it?
1.04.
Yeah. So
Yes,
even if you're getting a second shock, oblique shock, first of all, you can't get, so if I think about it, so the second time the flow gets deflected by 10 degrees or 9 degrees, and then you get another shock. Mm, something is wrong, man. Something seems wrong. Wait, because even then, wait. 1.4. What did you calculate a pressure value? Wrong, yeah. So wrong. What this?
no, I didn't. I think
If we consider twice or like once, if we consider it once, what happens when the
consider
flow is reflected? When there are two shocks, what happens then?
for just one oblique shock, P2 by P1
Hmm.
would be 1.67 ratio. P,
1.67, huh? Where, how did you get that?
no, I got frustrated from the tables, so I just opted for the
1
online
point,
calculator directly.
1.2. Oh, even
And
then, what value you used? This one, 1.67,
the
okay.
M1 was 1.45, wave angle 60, deflection 9.7, and pressure ratio it shows 1.673. 1.6, okay. P2 by P1. Then
Maybe this is static pressure only. If we consider that, okay. If we consider that, if it's a static pressure thing, wait. But how could it be static pressure, man? So weird. Okay, then you just okay. Then you find out the total pressure at the exit corresponding to 1.44, which will be what? Let me see. 1.67, you said, no? So 1.67 times 1 plus zero point 0.2 into 1.44 square is 2.36. Yes. Um, 1.647. Even then, you're getting 7.39. See, it's quite weird. This question is a little weird because the solution is also not fine. Options are 11, 13. Answer is 7. You have to solve this one properly. Okay, let's do it this way. Let's try to see if this is the static value. So that one more thing that I wanted to see was this: what happens when the two shocks this thing reflected wave. So maybe in this problem, we have to do this kind of situation, that we consider that there are two shocks um, coincide, and then you have to solve the angle of the second shocks. That also you need to consider if we do it properly. In like, did sir solve any of like such problems in the numerical videos? See, what did he solve? Don't think this is
I
too much.
so, but no, not. I don't think he solved the reflected stuff.
No, right?
There is no reference to such a question anywhere.
Anywhere, is it?
Yeah, you didn't solve such a question in any of the numerical what
Okay.
questions.
I'll try to solve it next time. I'll see if I can solve it. Um, Probably we need to consider this aspect also. The problem is that the Mach number was not very high at the exit of the duct. That is the problem I am thinking, uh, which um, and if we consider it as a static value, then what number you are getting, or what are you getting a number right now uh, for the P naught?
No, I'm not getting. I didn't solve any further.
See, at the exit, we know it's 1.44, right? Mach number will slow down to 1.0 something.
1.0504.
Then, yeah. So no matter what the another shock you have, it will only slightly drop the static pressure.
Weak shock,
What?
maybe. A very weak shock.
Very weak shock, yes. And even if we consider it to be 1 bar, all stagnation, this stagnation pressure and static pressure will also be well, um for a isentropic flow. What is P by P star near P by P naught near Mach 1? Close to Mach 1, P by P naught is okay. These things. So if we consider it as a static pressure, let's say uh, 1 bar is the static pressure. Let's consider it's open to atmosphere, so it's a pressure boundary condition. That's what. Uh, this is the free pressure boundary condition. Now, free pressure boundary implies that the static pressure is 1 bar. That is what. Maybe that's how you solve this problem. Wait. So this is somewhere. So what was written there? Free pressure boundary, right? Free pressure boundary is what? I think free pressure boundary implies that it's a static quantity. If that is the case, let's consider. Okay, that is something that we'll discuss later on. But let's say before, see, just after the shock, the static pressure is 1 ambient. Okay, 1 bar. Then the total pressure will be, because we essentially want to calculate P naught, which is the total quantity. So I will stick to this thing value. So it's 0.52, right? This one corresponding to Mach, because Mach number is close to 1 behind the oblique shock. P naught is 1 by 0.5283. Okay. And then using this table, we got a Mach number, normal Mach number of 1.27, I think. Isn't it? 1.27 or 1.24?
1.24, 1.247.
1.2, 1.247, which gives you the ratio close to
Actually,
0.98. So
I
P,
solved for the in sorry exit pressure, static pressure at the exit of nozzle. I'm getting something like 0.294 bar.
how did
We
you
can
solve it?
calculate. And I just used some calculators. No,
So
I'm
okay,
trusted.
you're saying at the exit of the duct
At the
or
exit of
exit
the
of
nozzle.
nozzle.
I Yeah, I took the pressure ratios.
So you got a at the exit of the nozzle, you got a 0.29 what? 0.29
0.294.
bar.
0.294 bar. Yeah. So P naught by
Okay.
P equals P.
So let that be. And Mach number also we know, right? 2.95. So let's find out the total pressure corresponding to 0.29 bar, 294 bar, right? If I do that, even then I don't think you will get a very high value. Let's see. So Mach number is
Oh, sorry,
2.9.
it's not 29. It's actually 21212. 29, 0.212 bar.
Okay. Order is same only, no? 2.94. 2.94, right? Mach number is 2.94, right? 2.95. So P by P naught. Maybe you can get a good value. So yes, so you were saying 0.21. What was it? 0.21
0.212 bar.
divided by 0.0298. We're getting 7.11.
Okay, I'm getting, yeah, I got 7 P not at 7 point something.
But still it's quite away from 11.
But the nearest to
It's
11.
still, but and I thought about it. Actually, the way I was thinking was the pressure is supposed to this stagnation pressure must be this high. It should increase because if you think about it, in a nozzle, as the nozzle moves downstream, your pressure static to stagnation pressure ratio keeps on decreasing, right? Maybe
Yeah,
it's a
yeah,
static pressure value because of the free bound pressure boundary. I didn't consider that because it's a free pressure boundary. The stagnation pressure will become static pressure in this region, right? Because pressure has to remain same. Like in a jet,
mm,
the stagnation pressure is
yeah,
equals to static
got it.
pressure. But 7.11 is, and that is the value I guess this guy is also getting in this solution, maybe. But still, the options are pretty weird. Pretty weird. Chalo, anyways. Okay. So what do I have now? Acha, I'll complete that whatever question I was doing, and then we'll stop. It's a small question. We'll stop. We'll see if we'll do Rayleigh flows later, or we'll see. So we'll solve one, two questions later on. So the question is, what is the Mach number of the maximum static temperature in a Rayleigh flow? Okay, so the question, should I repeat it again? The question is, what is the Mach number corresponding to the highest static temperature? So let's do that.
Okay,
And we can use these quantities themselves. This we can use this to just go and solve this value. So I'm gonna use this expression. It's a small derivation, nothing much. So if I use this, T is the inlet temperature, so that is not gonna vary. Sorry, T star is a constant value, so that is not gonna change. So T star is a constant thing. What you get is T star minus Tt by T equals to d of this entire thing. Um, I can take this thing out, and this one is twice of this value. Not no, no, no. 1 plus 1 by Mach square gamma divided by this entire thing. You get how did I come to this expression? There is n square, right? Can't simply just do this. So it'll be 1 by Mach square Mach plus gamma Mach. This one is fine, no? You understand this? This is fine or no?
think,
The way I have written this expression straight away. Probably there is a issue in under like the why have I how have I written this? Or is it clear? So the logic is,
Yeah, yeah, got that.
you got it, right? For
Yes.
the benefit of people who are maybe won't understand, if you have this expression, you simply get something of this sort: x dx, so x dy plus y dx equals to z dz. And now you subtract, differentiate this, divide the above equation from the second equation, so you'll get dy by y and dx by x equals to dz by z. So similarly, t star is a constant, so we don't differentiate that. We write t star dt by t. Then we write differentiation of this entire thing, divide by the entire thing itself. Mark square I took this, square I took inside. So now at the point of maximum temperature, dt by t will be 0. dt by t has to be 0. Wait, has to be 0, which implies that d1 by m plus gamma m is 0, and
So
this
that's a
is,
constant.
yeah, this is a constant. We can actually go further to write that minus 1 by m square is dm, plus gamma dm is 0, isn't it? Can we write that? Is this okay?
Yeah. Yes.
Right now, we know, what do we know? Yeah, now we know at the point, if we know the Fano flow curve, the maximum temperature occurs in the subsonic regime, and it um, will not occur at the point of sonic condition. It will be a little lower. That is something we know by intuition, and we'll have to do additional derivations to show that. But we know at least one thing, that dm is not 0 there. Mach number will will is supposed to change there, right? Why? Because Mach number is not approaching 1, supposedly. So in that, if we suppose that, then we know that this expression has to be 0, and then that will imply that Mach number should be equal to 1 by root gamma. Does this argument make sense? Let me think. Mach number not going to 0. DM change in Mach number is not going to 0. You remember the Mach number, change in Mach number goes to 0 only in the case of, in sonic conditions, right? Near sonic conditions.
Yeah.
Only then it will approach, or not asymptotically. It will approach to 0, I guess. We'll have to see. Hmm. Or we can simply see, if not that, it's actually the way I have derived it is a little uh, confusing. We can actually write the point of maximum temperature is supposed to be this. Rather than implying that dm is not going to be 0, we can simply say that at this condition, uh, we are going to get the maximum static temperature. And using this expression, we'll have to derive that. Okay, so if I do this, what I'm gonna get is T equals to uh, T star um, -2, -2 and -2. So again, now we can just write this, solve for this term, and then we are gonna get something of this sort. So loosely, I tried to solve it, but if you want to do it like ex- extensively or properly, you can start solving this thing. Again, not very like we can just simply do it here also. Let's see. Again, same thing. Mark and 1 by mark. This will be d by this thing, right? And now you can see it essentially this differentiation of this term has to go to 0 if we are doing this, right? So essentially you can see that again, a Mach number has to be 1 by square root of gamma to get you this expression. So this was one small, again, derivation. There is a small problem also, I think, on this same thing. Yeah, this one. So air enters at a given velocity and there is a static temperature and pressure given to you. You are asked how much heat must be given to create the maximum temperature. So this velocity corresponds to a Mach number of zero point 0.3. And if you solve for 1 by square root of gamma, you'll get a Mach number of, I think, zero point 0.8. Let me check. 1 by square root of zero point 0.8. No, no, not zero point 0.8, 1.1.14. Yeah, 0.84. So Mach of T max will be 0.84. And again, we will use this Q max quantity, Rayleigh flows. Give me a second. Yeah. So this table, in this Rayleigh flow, we are going to see what is T by T star, right? For different Mach numbers. So for a zero point 0.3 value, we can see if what is the Mach number at the inlet. And again, at the exit, we know we want the maximum static temperature. So that will be the value, and just Cp times T, this T we know. We can calculate T naught values for both of them and just subtract it and get a number. That was a small, again, substitution problem, not something very tricky or anything. So I had another like other questions where you will have area changes and normal shocks along with Rayleigh flows. So maybe we'll do that next time. Yeah, two more questions I had. Maybe we can do it next time. We'll see. I'll also see, try to solve this question. Wait, of the fan flow. We'll see if, but I think 7.11 is fine because Mach number is a little low at the exit. But then why are the options so weird? That is something that maybe we'll have to see. Because 7 and 11 is very
Mm.
different. Does not
Hmm.
make sense for the options to be that far away. But anyways, we'll see.
And
Sometimes there
sir,
are questions.
sorry,
Yes. No, no, go ahead.
no, no, I was just saying that in the Excel sheet of uh, the YouTube links for the recordings, I think more.
Hmm.
I think some of the lectures are like we cannot open those links. If I open
Is
it,
it
it
so?
says the video isn't available anymore. It says,
Wait, wait, wait. Let me check that. Check
like
for that.
for week 9, I am able to see, but for week 8, I think week 7.
Week 8 you're not able to open, is it?
No, no, I think more than that.
Oh,
Six,
multiple
seven, eight.
ones.
Yeah, 6, 7, 8. Maybe three. No, not three.
Okay,
Six, seven,
what's
eight.
wrong,
Yeah.
man? Video isn't available anymore. Why is that? Wait, let me check. YouTube. Why is that? 678, huh?
Yeah, I think you should stop your screen sharing during.
You're saying I should stop screen sharing, is it?
Yeah, I mean you're actually in your YouTube account. That's why I was saying because that's getting
That's
recorded.
fine. That's okay. Let me. Why is it not there? I can stop recording maybe. Wait. There's no point of recording all this. Processing video could not be processed. Why? Okay, I'll check that. It seems that there are issues. I'll update these things. 678, no? I'll do this.
Yes.
Video failed to upload. Okay. Okay, I'll do this. Thanks. Thanks for letting me know.
Yes.
Yeah. So yeah. Let's meet next week. Fine.